So the next chapter that we'll be covering, guys, is rotational kinematics. So we're going to be returning to the kinematic equations that we started the year with, except now we're going to consider objects that instead of moving translationally, in other words, moving in a line or as a parabola, we're going to consider objects that are rotating in space. So this is kind of similar to the circular motion that we did before. But we're going to actually kind of quantify the spinning motion of the object in terms of different quantities. So when we look at spinning objects, say I have the circle here, right? I can mark a point on the circle, and so this little blue dot here. And again, kind of the issue we're having is that as the circle rotates around, eventually this blue dot's going to get back to where it started from. And so it would have like a linear displacement of 0, right? Because it started and ended at the same spot. And yet this dot did move. There's motion going on. There's rotational motion going on. So as this dot goes around, okay, it spins around and it returns back to where it was, but we know that it has gone through kind of like this full rotation here. And so we can quantify how much rotation it went through by measuring the angle, essentially. So you have this origin point right here, and you can measure the angle that it has spun through. So it can go from there to here to here to here, and the greater the angle is, the more displacement it has had. So what we do is we measure their angle. Okay, so look at this, right? So say it goes from right here and it spins around and goes right there. So measuring from the center, okay, we'll say it has rotated through some angle theta. Okay, so it's measured, we're going to measure this rotational displacement using this angle, and we'll call this angle theta. In fact, we're going to use fancy Greek symbols for all these different quantities. And so this is going to rotate around, and we can quantify how much it rotated by expressing the angle that it swept out. The units that we're going to use for this angle will be in radians. Okay, so we're going to express our angle in radians. And I'll show you why that is. We're just not trying to screw with you. But there's a good reason why we use radians, which I'll show you in a little bit. But you can imagine that as this turns around and around and around, we can measure not only the angle that it has swept out, but maybe how quickly it swept that angle out. It could be going very slowly, okay, or it could go very quickly, okay, and we want to quantify that. How quickly did it sweep out the angle? What angle did it sweep out? Is the rate that sweeping out the angle changing? And all these are the quantities that we're going to use to express this rotational motion. So what we're going to see is that there's a lot of similarities between linear and rotational quantities. So let's start with this idea of displacement, which we already looked at. This is the angle, being swept out in rotation motion. So what we would have is instead of using r, we're going to use this angle theta. That's a bad theta. Let me redo the theta. So we're going to have this idea of theta. So this is going to be what's called my angular displacement. Angular displacement. Okay. And so if I have a circle here, and again, I go from there and I sweep out this way, then I can measure some angle theta that it has swept out. But the other thing I can do is realize that there's this translational part, the arc length. Okay, so there's also certain arc length that it has swept out too. So if this was a wheel rolling along the ground, I can specify this angle theta that the wheel has turned through, and this arc length will be how far. I call my arc length S here. So this arc length would be how far the wheel has turned through. And the cool thing about using radians, and this is why we use radians, is that I can say that the arc length that I swept out will be equal to my angular displacement theta times r, where r is the radius. Okay, so if I use radians, I can say these cool things. I can relate the arc length to the angular displacement theta, and this radius r. Okay, so this is one kind of relationship that we can make between our angular displacement and this arc length s. That, that's going to be more of this linear displacement along the edge here. Then we have velocity. Okay, so we can talk about the rate that these angles are being swept out, as I said before. So we will call this, again, we use fancy Greek letters for all this, so we call this omega, and this is velocity. Okay, so mathematically it'll be the change in theta, the angle that we've swept out, over the change in time, or to put it in words, the rate that the angle is being swept out. Okay, swept out. Okay, so you can think of it of the angular velocity that way. This will be essentially how fast is it spinning, and you can relate this to the linear velocity. So essentially how fast this dot's moving translationally around the circumference. Okay, that this is going to be omega r. So again, we have this idea we can get the linear quantity if we take the angular quantity and we multiply it by the radius, as long as we use radians for this. Okay, I want to emphasize that. And then finally, our favorite, acceleration. It was hard enough to understand this when we were doing like the linear motion that we're familiar with, but we also have to understand it in terms of angular motion. So we're going to use alpha. Oops, sorry. Okay, we're going to use alpha for this. And this will be our angular velocity. Angular acceleration. So this will be our angular acceleration. And just as the linear acceleration is the rate that the velocity is changing, the angular acceleration is the rate that the angular velocity is changing. So you can imagine that if this wheel doesn't turn at a constant rate, maybe it starts from rest and then it speeds up, okay? Or it's going and then it slows down. Okay, if the rate that the angular velocity is occurring changes, then we have an angular acceleration. So this angular acceleration, mathematically, change in angular velocity over change in time. Okay, and this will occur. So this will occur when rotation. Wow, that's a really bad spelling. When rotation speeds up or slows down. Okay, and once again, we can talk about this translational acceleration by saying that it's the angular acceleration times r. Okay, so these three equations here allow us to translate between angular quantities and how fast it's being translated, the rate that it's being translated, the change in the rate it's being translated. All that will be related by these three equations right here. Okay, and then the last thing I'm going to tell you guys in this video is that because there's such similarities between these two, this is good news. All of these translational kinematic equations that you guys, put so much effort into learning how to use in the first chapter, we'll use them again. We'll just be replacing all of these linear quantities with the angular quantities. So this tells me the displacement of an object, right? So say I have an acceleration going from point A to point B, and I have a certain amount of time that it occurs, I can get the change in displacement that occurs there. What this equation will allow me to do is it'll allow me to calculate how many radians, okay, was swept out given the acceleration. So maybe I was speeding up or slowing down, and the time over which this angular acceleration occurs. So they work the same way. I think the trick is just being able to kind of wrap your mind around this whole idea of rotational motion, that an object rotating, which it's not quite as easy to see the displacement and the velocity in the angular acceleration in that case. But I believe in you guys. I think you can do it. I know you can do it. Okay. Oh, one more thing before I sign off here. You know how before